The sensitive plant. Touch a single leaflet of Mimosa pudica, and the entire leaf folds shut within about a second, the whole stem drooping downward as though the plant had suddenly wilted before straightening back out minutes later, completely unharmed. That fold happens through a structure called the pulvinus, a swollen joint at the base of each leaflet where specialized cells rapidly pump out potassium and chloride ions the moment they sense mechanical disturbance, causing water to rush out of those cells and collapse their internal pressure almost instantly. In 2022, researchers using fluorescent calcium sensors finally caught the actual trigger signal in action, watching a wave of calcium race from the point of contact through the plant and reach the pulvinus in under 1/10 of a second, faster than the folding response itself. This is not simply a curious party trick. Controlled studies comparing normal plants against ones genetically altered to lose their folding ability found that immobilized plants suffered roughly twice as much damage from grasshoppers and caterpillars, confirming the collapse genuinely startles or deters browsing insects by making the plant look suddenly smaller and less appetizing. The same plant folds every single night regardless of touch, following an internal clock separate entirely from its touch response, meaning a sensitive plant left completely alone will still visibly droop and reopen on its own daily schedule. Native to Central and South America, but now naturalized across warm regions worldwide, the plant carries small spines along its stems that become far more exposed and visible the instant a threatened leaf folds shut, adding a second layer of defense right behind the initial startle response. The Telegraph Plant. Unlike almost every other plant capable of movement, Cadariocalyx motorius does not wait for a touch, a sunrise, or any outside trigger at all, since its small side leaflets rotate continuously through tight elliptical loops roughly once every 3 to 4 minutes, all day long, with no stimulus required whatsoever. Charles Darwin himself studied this species in the final years of his life, fascinated by movement visible to the naked eye without any time-lapse camera needed, a rarity among plants capable of any kind of motion. Every entry on this list represents a genuinely different mechanical strategy plants have evolved for movement, and Garden's lab keeps tracking down species this visually strange for a new deep dive every few days, since almost none of these mechanisms work the same way twice. Researchers have documented that the plant's dancing accelerates measurably when exposed to certain high-pitched sounds and music, a discovery that spread widely online through countless viral videos, even though the underlying biological reason for that sound sensitivity remains genuinely unresolved among scientists studying the species. Despite generations of curiosity, from Darwin's original notes through modern electrophysiology studies measuring the leaflet's internal electrical rhythm, researchers still cannot fully explain why this particular plant evolved constant, purposeless-seeming motion at all. The prayer plant. Every single day, without fail, the broad patterned leaves of Maranta leucanura lie completely flat to soak up maximum light, and every single evening, those same leaves rise and fold upward into a shape resembling two hands pressed together in prayer, giving the plant its common name. That rhythmic rise and fall runs on a genuine 24-hour internal clock rather than a simple reaction to darkness, driven by the same pulvinus joint mechanism found in the sensitive plant, here responding to a circadian rhythm instead of touch. Scientists believe the nightly folding reduces water loss during the cooler overnight hours and may also help shield the leaf's more vulnerable underside from nocturnal insects looking for an easy meal in the dark. Because this movement depends on stable light cycles and consistent hydration, a healthy prayer plant that suddenly stops folding at night is often signaling real physiological stress well before any other visible symptom like yellowing or wilting appears. Time-lapse footage of the plant across a full 60-hour stretch reveals just how constant and rhythmic the motion really is. The leaves rising and falling in a slow, steady pulse that never actually stops for more than a moment throughout the plant's entire life. Native to the rainforest floor of Brazil, the species evolved this rhythm in an environment where filtered light already changes dramatically throughout the day, making a plant finely tuned to tracking those shifts a genuine survival advantage rather than simply a decorative quirk. The touch-me-not, brush against a ripe seed pod on Impatiens capensis, commonly called jewelweed, and the entire capsule explodes apart in a matter of milliseconds, its 5 outer valves violently coiling inward and flinging seeds outward in every direction at once. Laboratory measurements have clocked the complete process, from initial trigger to final coiled collapse, at somewhere between 3.8 and 4.6 milliseconds, faster than a human eye can meaningfully track without high-speed camera equipment. That explosive force comes from mechanical tension stored directly in the hydrated tissue of the pod wall itself, and researchers measuring its energy storage capacity found it comparable, pound for pound, to elastin and even spring steel. Seeds launched from a single popped pod can travel over 2 meters from the parent plant, launched at an angle mathematically close to the exact trajectory that would maximize total dispersal distance according to a pure ballistic model. Children across generations have delighted in seeking out ripe jewelweed pods specifically to trigger this reaction, turning what is fundamentally a sophisticated seed dispersal mechanism into one of the most reliably entertaining discoveries a walk through damp woodland can offer. The sunflower. Long before a sunflower field opens into its iconic wall of golden east-facing blooms, the young, still-growing plants spend weeks performing a much stranger daily routine, leaning steadily westward to track the sun throughout the day before swinging back to face east again overnight in anticipation of the following dawn. Researchers confirmed this solar tracking runs on an internal circadian clock rather than pure reflexive response to light, since young sunflowers kept in constant indoor lighting with no directional sun cue at all continued the same daily east-west swinging rhythm purely from internal timing alone. As the flower head matures and finally opens, that nightly movement stops entirely, locking the bloom permanently facing east. And researchers discovered that east-facing flowers run measurably warmer in the morning sun than west-facing ones, a heat difference that noticeably attracts more pollinating insects. Disrupting that natural tracking rhythm carries a real biological cost, and one field experiment that forcibly rotated young plants against their preferred direction each evening measured a meaningful drop in both total plant biomass and leaf area compared to undisturbed controls. What looks like a simple, almost decorative habit turns out to be a precisely regulated growth strategy balancing maximum photosynthesis during youth against maximum pollinator attraction once flowering finally begins. The resurrection plant. For most of the year, Selaginella lepidophylla looks completely dead, curled into a tight, dry brown ball barely larger than a fist. And yet a single soaking in water is enough to bring the entire plant back to vivid green life within just a few hours. This desert spike moss can lose as much as 97% of its internal water content and survive the ordeal with barely any permanent cellular damage, a level of desiccation tolerance that would be fatal almost instantly to the vast majority of plants on Earth. Once rehydrated, the plant's cells begin rebuilding the chloroplasts and photosynthetic enzymes that broke down during dormancy, restarting food production from sunlight within hours of the very first drop of water reaching its tissue. Researchers studying the physical mechanics behind the curling motion determined the process is driven almost entirely by passive structural changes in the stem tissue itself, rather than any active biological signaling, meaning even portions of dead, non-living tissue on the plant still curl and uncurl correctly on cue. That tight, ball-shaped curl also serves a second defensive purpose beyond simple survival, physically blocking more than 99% of solar radiation from ever reaching the plant's more vulnerable inner stems during the harshest, driest stretches of desert heat. Native to the Chihuahuan Desert spanning Mexico and the southwestern United States, individual plants have reportedly survived years or even decades in their dried, dormant state, before finally encountering enough water to trigger a full and complete revival. The Barberry. Nectar-drinking insects visiting a barberry flower get more than they bargained for the instant their tongue brushes against one of the plant's touch-sensitive stamens, which snap forward in a fraction of a second and slap a fresh coating of pollen directly onto the startled visitor's face or tongue. Researchers who experimentally immobilized these stamens found that insects lingered up to 3.5 times longer at each flower when the snapping mechanism was disabled. Yet those same insects ended up carrying meaningfully less pollen away and depositing far less of it onto other flowers' stigmas. That counterintuitive result reveals the real evolutionary purpose behind the ambush-like mechanism. Since startling a pollinator into leaving quickly, rather than letting it linger and overfeed at a single bloom, actually spreads far more pollen across many more flowers across an entire shrub. This precise touch-triggered motion has fascinated scientists for centuries, first formally documented by Carl Linnaeus himself back in 1755, making it one of the earliest recorded examples of rapid plant movement anywhere in scientific literature. Because the trigger point sits specifically at the base of each stamen's filament, only a direct touch in exactly the right spot sets off the snap, sparing the flower from wasting its single-use pollen delivery on wind or random passing debris. Related plants in the genus Mahonia share this same touch-triggered stamen mechanism, suggesting the trait evolved once in a shared ancestor rather than independently across each species that displays it today. The tumbleweed. Rather than moving a single leaf or petal, Salsola tragus, commonly known as Russian thistle or simply tumbleweed, takes the far more dramatic approach of moving its entire body once its job of growing and flowering is finally finished. As autumn arrives, the mature plant dries out completely and snaps free from its own root system right at the base, transforming from a rooted, bushy shrub into a light, hollow, wind-driven sphere capable of rolling across open ground for remarkable distances. A satellite tracking study following individual tumbleweeds across working wheat fields recorded one plant traveling more than 4,000 meters in just 6 weeks, its path correlating almost perfectly with shifting wind direction the entire way. That constant tumbling motion exists purely to scatter seeds as widely and randomly as possible, and a single mature plant can carry up to 250,000 seeds at once, releasing a steady trail of them with every bounce and roll across the landscape. Introduced accidentally into South Dakota through contaminated flax seed back in the 1870s, this Eurasian native spread coast to coast within just a few decades, turning its own unique method of movement into one of the most effective invasive colonization strategies any plant species has ever demonstrated. Now firmly woven into American cultural imagery of the arid West despite its foreign origins, the plant continues rolling across roadways and open fields today, exactly as it did more than a century ago, still spreading seed the same simple wind-powered way.